I will present this work titled Numerical Simulation of Laser Shock Disassembly for Adhesively Bonded CFRP metallic parts from coupon scale to structural part level. And this is the work conducted in the frame of Morpho project. This is an outline of my presentation, and first I will briefly talk about the aircraft end of life and some laser shock introduction, similarly to what Dr. Bert already told you. And after that, I will move to the numerical procedure, which includes the numerical implementation of a multiple shot process, and then the finite element models, both in a detailed format and homogenized format for coupon and structural part level. So according to Airbus's Pamela report, 85% of the materials from aircraft nearing their end of life in 2008 could be recovered, and specifically 15% of those materials could be reused, while 70% could be recycled. However, composite materials now make up more than 50% of the total weight of the modern aircraft, which poses a challenge, and the traditional end of life of aircraft structures needs to change, and especially since the main form of joining composites is adhesive bonding. As illustrated here on in the end-of-life processes diagram of an aircraft, the separation of materials is a crucial stage, and the quality of end-of-life products heavily depends on this stage. Currently, industrial material separation strategies are chosen based on the cost-benefit analysis, and the two extremes are systematic disassembly, which involves the precise separation of all connections, and shredding, where each section may contain several different materials. And typically, depending on the composition of an aircraft section, intermediate techniques are used, as they can be seen here, although these strategies fall short when it comes to disassembling of bonded structures. And this poses a significant challenge, particularly when different high-valued materials are joined together. The proposal studied in the Morpho project concerns the disassembly of bonded structures using the laser shock technique. And as Laurent already mentioned, laser shock is a technique based on laser-matter interaction. And when a high-powered laser is focused on the material surface, it generates plasma that rapidly expands and exerting pressure on the material. This plasma expansion can be confined using a dielectric material that is transparent to the laser, and this further increases the generated pressure. Now, this rapid increase in pressure creates a compressive shock wave that travels inside the material, and upon reaching its back face, the opposite surface, it reflects back as a tensile wave, also called the release wave in literature. And at the same time, due to the surface unloading, on the top surface, another release wave is propagating inside the material. Now, the interaction between those two release waves results in high tensile stresses, and their relocation can be challenging to control because it depends on the laser characteristics and the material properties. So different configurations are used, such as the symmetric laser shock configuration and the double shot. A lot of techniques Laurent already mentioned. Now, for the Morpho project, the laser shock process is studied for the disassembly of a foreign object damage panel. And this is the demonstrator platform of the Morpho project. And the FOD panel is a representative structure of a cord of a multi-material engine fan blade at a specific cross-section. And it is composed of a 3D woven composite core bonded to a thin titanium protective layer at its leading edge. And the goal of the disassembly process is to separate the titanium leading edge from the composite core. Now, the simulation of the disassembly process on the FOD can be described in 3 steps. Initially, the automated multi-step simulation procedure is developed and implemented using the Python script. Then follows the coupon scale simulations that are validated by experimental data. And finally, the process is upscaled numerically to a structural part, and the full disassembly simulation is conducted. To achieve these various experimental data and results were utilized for the development and validation of the finite element model, and specifically dynamic punch shear and tension experiments using the split Hobkinson apparatus provided material properties for the 3D woven composite structure. And after that, single and symmetric lasers of experiments were used to validate the results of the numerical simulation at coupon scale. Now, in order to implement the laser shot technique as a disassembly process, it is required to execute multiple consecutive shots, either at the same location or adjacent locations. And during the simulation, using the LS-DYNA explicit finite element code, it is possible to use the output of a simulation as an input for a subsequent one, and thus facilitating a multi-step process. And because this process can be quite time-consuming, a subroutine was developed using a Python programming language to automate a series of analyses. And this subroutine takes as an input two K files from two models, essentially, and a table as a CSV format that describes all the subsequent loadings that are used. Now, the simulation of the loading to produce a shockwave is performed by applying pressure on the material surface, and the pressure follows a Gaussian temporal profile, as it is illustrated here, while the maximum pressure can be calculated using this equation, where alpha is Pmax is the maximum pressure, and alpha is a variable that describes the amount of energy, the laser energy that is required to ionize the plasma, and it is a material-dependent property. Z is the relative acoustic impedance between the plasma and the confining material, and I0 is the laser intensity. Spatially, the pressure is assumed to be uniform across the entire surface of the circular spot, and this assumption is based on the fact that the spatial profile of the laser intensity after passing through a diffractive optical element is uniform, as it is indicated by the blue line in the spatial intensity plot. The complex 3D architecture of the composite core requires further investigation for the simulation procedure, so a detailed 3D woven model was designed and compared to a more traditional homogenized finite element model, and the design of the detailed 3D woven model was done using the TextGen software, where a custom script was used for the generation of the geometry. The 3D woven architecture is composed of two parts: the bulk of the material, which utilizes a standard layer-to-layer woven approach, and the top and bottom surfaces, which use a non-standard woven pattern that had to be designed separately using a script. Now, the geometry was meshed using voxel elements, and in order to observe the influence of the mesh density, part of the geometry was meshed using different mesh sizes, and the backface velocity was measured and compared. Due to the small observed differences, the most computationally efficient mesh was chosen, which is the R1 that can be seen here. The fiber bundles are modeled as a high fiber content composite material, and the properties were computed using Chams's micromechanical equations and applied to a progressive damage model that uses Hassin type failure criteria and has formulators for strain rate dependencies. Additionally, for every bundle, the material direction was defined separately, as it is seen here. For the simulation of the matrix, an elastic plastic material model was used, and considering that only the elastic modulus and the max stress and fracture strain are known for the polymer, the yield stress is assumed to be at the 30% of the fracture strain. And due to the high strain rate of the laser shock loading, material properties have to be modified accordingly, and this is done by the same logarithmic law that is applied to the fiber bundles. Strain rate data for the matrix material are not available in literature, and for the calculation of the strain rate dependent coefficients, data for a similar epoxy was used, and the fitting can be seen here. And this is the final curve that is used for the simulation. Additionally, homogenized model was used for using the same geometric characteristics and meshing as the detailed one, and the material model is MAT 162, which is a progressive damage model. And the properties have been derived from dynamic characterization experiments of the material in combination to some literature data. Now, the comparison of the shock waves is initially done by the z-axis stress, and in the figures, the compressive stresses are depicted in blue, while the tensile in red. For both models, it can be seen that it is observed that they have a similar propagation speed at all timestamps. And additionally, the interaction between the two release waves during the 4 microsecond mark, it appears to be identical in both models, and the main differences can be found on the boundaries of the waves where stresses are lower. Next, two spots of the detailed model were compared by the same means, and one spot appears to have a higher density of binder bundles and has an increased number of localized reflections. And as it is observed by the dotted boxes here. Comparing the backphase velocity of the two spots and the detailed model and the homogenized model indicates that the 3 initial peaks arrive at the same time, but the peak value is different due to differences in localized reflections. Finally, comparison of the damage prediction between the homogenized and the detailed model shows that the detailed model is more accurate in the prediction of the location of the damaged areas. And the detailed model predicts a small localized fiber damage close to the damaged area, and the homogenized model did not predict that. But the homogenized model was found to be more efficient for the goal of disassembly, so it was chosen over the detailed one for its efficiency. So 2 homogenized models at Kuban scale were developed in order to simulate the laser shock experimental procedure. And one is used for the single pulses and one for the symmetric pulse experiments. And both models are replicas of the specimens and contain the 3D woven composite core using the homogenized model that was presented earlier. And it is bonded to a titanium layer that is simulated by the Johnson-Cook material model in combination with the Grunaysian equation of state. And the material properties have been obtained from literature, as it is a well-studied material for high-strain applications. The bond is simulated using the cohesive zone method. The simulation procedure can be described in 3 stages. Initially, single pulse shots were simulated and backphase velocities were compared to experimental velocities. Then the symmetric laser shock loadings were simulated for 4 successive shots in 2 spots, like the experimental procedure, and the debonding predicted by the model is then compared to the experimental debonding. And finally, the validated model is used to simulate an extended debonding using 16 shots at 8 spots of the specimen. The comparison of backphase velocities obtained from the simulation for laser intensities 4.5 and 6 gigawatts per centimeter square show agreement with experimental measurements for the first 2 peaks, which are the most important ones for the use of the shock wave for disassembly. And here is a video of the propagation of the shock wave inside the specimen. This is the z-axis stress that we are observing here. And 2 distinct waves can be seen in the simulation and also in experimental observations. And their generation can be seen here. Now the simulation of the symmetric pulse caused the debonding that is presented here as cohesive zone erosion. And this is a comparison of the simulation results to the experimental debonding process. The first shot causes a plastic deformation at the bond line of the titanium and the composite. And this can be seen by the model as effective plastic strain, meaning the damaged state of the cohesive zone by this plot. The second shot initiates the debonding with a length of 2.4 millimeters, and the model predicts a debonding of 2.26 millimeters, as it can be seen here by the deleted elements in blue. And then the spot is moved by 2 millimeters and shot again 2 more times, and the final debonding is 3.9 millimeters, while the model predicts a debonding of 4.3 millimeters. Now, the results of the extended debonding show that the progressive erosion of the cohesive zone at the top view of the at the top view here, and the matrix damage on the side view that can be seen here, but no fiber damage was predicted by the progressive damage model. The disassembly of the FOD panel, separating the titanium part from the composite, is achieved by a numerical upscaling of this process that was described here, and the upscaling procedure is the following. First, a preliminary study was conducted on an inclined surface. Then a finite element model of the FOD panel was designed, and the simulation process was carried out in two phases. The first phase involved defining the process by calculating the time delays for the detachment of the upper and the lower faces, and the second phase focused on the simulation of the complete debonding of the titanium, utilizing an automated simulation procedure that was described earlier. The preliminary simulation of an inclined geometry was conducted to examine the effects of the spot geometry, alteration in the generation and propagation of shockwave. And the simulation specifically include a circular spot where the beam remains parallel to the surface, and an elliptical spot, and a second elliptical spot. Given the negligible differences in the backface velocity measurements, it is considered that no additional measures are necessary for the disassembly of the FOD panel. For the simulation of the FOD panel, a strip of the full geometry was used, and it utilizes the same material models as the validated at coupon scale model. And before simulating the entire debonding process, preliminary simulations are conducted for process design, and specifically the double pulse technique was applied to the same side of the component with a time delay. And initially, the upper interface of the panel is targeted in order to achieve a complete debonding, and the newly created surface can be used for the debonding of the bottom interface, as it is observed here. To achieve this, 4 points of the panel are selected, and the time delays for each point are calculated. And after that, after setting the time delays, the FOD is subjected to 29 consecutive shots at 14 predefined locations to completely debond the structure. The simulation results initially show debonding of the upper interface using a constant time delay, but for the debonding of the lower interface, the wave propagation should be observed, and this creates 4 individual time delays for the spots, and they are interpolated using a second-order polynomial equation to find intermediate delay times. And applying the findings of the process definition simulations, the complete debonding of the FOD strip was achieved. And the figure here shows the cohesive zone of the panel that is gradually eroding. First the upper interface, followed by the bottom interface. And this is the final structure where some residual adhesive can be observed at the tip of the structure. This cannot be targeted by the laser shock. Yes, and finally, the damage that was predicted by the progressive damage model is presented here, and this is matrix damage parallel and perpendicular and parallel to the fibers, while no fiber damage was observed during the simulations. And some conclusions, the complexity of the materials required some advanced simulation techniques and new ways to employ the LSDyn explicit finite element code, and specifically the development of a multi-step simulation procedure for extended debonding simulation reduced significantly the computational time. The development and comparison of the detailed 3D woven composite to a traditional homogenized one, where shockwave propagation observations revealed minor differences between the two models, while the detailed model provided more resolution to the damage prediction. Finally, a homogenized model utilizing state-of-the-art progressive damage model that facilitates high strain rate dependency coefficients was able to predict the laser shock mechanisms that are utilized for the disassembly of the FOD panel. Upscaling of the process. Initially, some preliminary investigations of the inclined geometry revealed that the spot geometry alterations are minor, and the process definition simulation for the disassembly revealed that in order to debond the top interface between the titanium and the composite core, a constant time delay suffices. On the contrary, the debonding of the bottom interface depends on the varying thickness of the composite substrate and has to be individually calculated using a second-order polynomial equation. Finally, the full disassembly of a 10 mm strip can be achieved by 29 consecutive shots, and during this process the composite is damaged, but it is confined to matrix cracking only, while the fibers remain intact. Thank you very much for your attention.